Hello engineers, welcome to the Formula Engineering classroom. And after understanding the concept of Pascal's law and hydrostatic law, in this lecture we will understand the concept of pressure measurement. So the device particularly used for the pressure measurement we normally termed as manometers. There are so many other devices, but in this lecture we are about to discuss of manometers. But to understanding the manometers, we have to understand before this one, that is the any pressure measurement device have to follow these three things. That is, first of all, it will follow the Pascal's law. Obviously, we know the Pascal's law, that is pressure intensity at a point in a static fluid is same everywhere. Second, it will follow the hydrostatic law. So we know that is hydrostatic law is what means, that is the pressure keeps increasing with the increasing in depth under fluid. And third point is pressure doesn't affect by the boundary. So what is the sense of this term? So in last lecture we discussed about the hydrostatic paradox, and in that lecture we saw that there is the boundary of the container is changing the pressure force that is exerted by the fluid, but that was the pressure force, not the pressure intensity, because according to hydrostatic law we know there is P equals to rho GH, and this pressure intensity have no effect of area. That's why I'm using the word boundary. In this formula the only term is the height and there is no effect of the area. So if any device following these three things, then we can use the device for the pressure measurement. So in pressure measurement category, our first device that we are using, that is termed as piezometer. That is termed as, I'm writing here, this is first one we are defining. Sorry, this is piezometer. So what is piezometer? So to understand the piezometer, let's take a look of this example. So let's suppose we have a tank here. I will try to make in 3D. Okay, so this is the tank. Okay, that looks good. Now, and let's suppose there's an opening here, and let's suppose here I'm attaching a pipe. Okay, that's good. Now this is the center of pipe, and this is the center line that is passing through the pipe center. Okay, now this container is filled with some particular fluid. This is filled with some particular fluid here, over here. Okay, and let's suppose the height of the free surface of this fluid from this center line is, let's suppose we are saying this is h. Okay, and the density of this fluid we can say this is rho. So if I want to calculate the pressure intensity at the center of the pipe, so by using the hydrostatic law you can easily tell that is what will be the pressure at this point. Obviously in this case, as the height of the water above the center line is h and the density of this fluid is rho, so pressure, let's suppose if I'm saying this point is a point, so the pressure at the point A will be equals to rho g h a. I'm indicating the suffix here, a here, that is h a is the height from the point A. Okay, so this is the pressure intensity. So obviously, as we discussed in the previous lectures, that is, this pressure intensity is only gauge pressure intensity. Obviously, over the free surface of this fluid, there is atmospheric pressure. This is PATM, but PATM we are considering 0, as we are taking this is gauge value, because the P atmospheric is everywhere. So at this point, the gauge pressure value is rho GHA. Okay, so this is, we know that the pressure at the point is rho GHA, and we can calculate easily if we know the density of fluid and if we know what is the height of the fluid surface, free surface, from the point A. Now, so how the piezometer will work? So piezometer is nothing, it's a simply straight transparent glass tube. It's a straight transparent glass tube. Obviously this is not looking straight here, but no problem. So this is a straight transparent glass tube. Okay, and this side is open to atmosphere, and this side of this tube, glass tube, is connected where we want to measure the pressure. Let this is the cross section of pipe, and in this case, sorry, this is, let we are saying this is the center of this point. Let I'm saying this is A, and obviously there is some fluid in this pipe here. Okay, so if I'm connecting a pipe over here, in this case we connected the pipe to the tank here, and if I connect a piezometer to this pipe, that I'm connecting this piezometer over here. Okay, this end is connected to the pipe. So in this case, this fluid will try to level itself, and the fluid level will rise in this tube over here. So the fluid is rising, leveling itself up to this point, and obviously in this case, the height of free surface of fluid in this tube that we are defining piezometer will be exactly equals to HA from this point A. This will also be equals to HA from this point A, as the fluid will try to level itself. So in this case, the fluid will rise up to the height H A from the point A. So in this case, I think by measuring this height HA in this tube, we can easily calculate what is the pressure intensity at this point A. So obviously we can write that is PA is equals to rho GHA, and this pressure will be gauge pressure. I can write this is gauge pressure. Okay, so this is a simple straight transparent glass tube, and let's suppose if I want to calculate the pressure intensity at this point B. So first of all, I will measure the height of free surface of fluid from the point B. Let's suppose this is HB, and then we can easily measure, and we can write that is PB, that is pressure at the point B will be equals to rho GHB. So it's very much simple. By using the hydrostatic law, we can easily tell what is the pressure at the point A and B, and these points A and B are termed as gauge points. Means the pressure we want to measure at that particular point, and the pressure is as the gauge pressure. We are defining these points are the gauge points. Means the pressure intensity at the gauge point A is equal to rho GHA, and the pressure intensity at the gauge point B is the rho GHB. Okay, so I think this is clear now. But there is some problem. The application of piezometer is limited. There are some demerit of piezometer. First of all, piezometer can't use to measure excess pressure. Now what is the sense of this term? There is the excess pressure. So let's suppose the height of the fluid in this tank is 1 meter. I'm saying this is 1 meter. So in this case, when the height of this fluid in this tank is 1 meter, in that case we required the height of piezometric tube should be greater than 1 meter, and obviously we can't carry a tube that has height of 1 meter that is specially made of glass. So obviously in this case the piezometer will be used only for the small pressure measurements. Obviously in this case, when the height is 1 meter, the tube is very much long, you can't carry them. So the first problem is that the piezometer can't be used to measure the excess pressure. Now the second problem is that, let's suppose this fluid is some gas. Obviously in this case the tank is closed. The tank is closed here, and this fluid is some gas. So when you attach this piezometer to this tube or pipe, in that case, as the gas definitely will move out from this tube, and obviously the gaseous fluid doesn't matter the free surface, you can't measure the height. So if you can't measure the height, you can't measure the pressure at all. So the piezometers also can't be used to measure gaseous fluid pressure. Okay. Third problem is that piezometer also can't be used to measure negative gauge pressure. Negative gauge pressure means vacuum pressure. Means, let's suppose in this tank somehow, as the tank is closed, we maintain some negative gauge pressure. So negative gauge pressure means the pressure is below atmosphere. Okay. So when the pressure is below atmosphere in this tank, and when you attach this tube, this piezometric tube, to this pipe, in that case, as the pressure in the pipe is less than the atmosphere, and this end of this tube is open to atmosphere, that is the higher than this pipe pressure, then the air will rush in this tube. Okay. So in this case also we don't have any significant height rise of fluid because there is a vacuum pressure. So you can't measure the pressure by the use of piezometer for the negative or vacuum pressures. That's why we will move to our next device, that is termed as Utube Manometer. So let's take a look to a new improved device that we defined, Utube Manometer. So our new device is Utube Manometer. Okay, so what is Utube Manometer? So as in case of piezometer, we defined this is a straight transparent glass tube. Utube actually a glass tube, this straight, this is not straight, it's a transparent glass tube bent in U shape. So it is look like this. This is a transparent glass tube and bent in U shape. Okay. And initially that we are saying that is both the ends are open to atmosphere. Okay. Now in case of piezometer, there was no manometric fluid. What is the sense of manometric fluid? So actually manometric fluid is like thermometric fluid. Means in case of piezometer, the flowing fluid in the pipe was rise in the tube, and there was no other fluid. But in case of manometer, we initially have some other fluid. That's what I'm saying. This is some another fluid. Okay, the not looking good, but I think you can understand this one. So this is some another fluid, and we are defining this is manometric fluid. This is manometric fluid, and obviously in this case the properties of this manometric fluid are known. So that we are saying the specific weight of this manometric fluid is small w suffix m. This is a specific weight. So obviously in this case, when initially this Utube manometer is open to atmosphere, on both the limbs, I am saying this is left limb, and this is a right limb. The level of manometric fluid will be same as both sides are open to atmosphere and atmospheric pressure is exerted both sides. Okay, so obviously in this case this is a fluid, so the leveling, it will try to make a level. So the level both side in both limbs will be same. So let we are saying this is 1, 2. Okay, now so in this case we are using a different fluid that is defined as manometric fluid. Now we are connecting this this Utube manometer to some pipe. In that pipe, at the point A there is some pressure, because we know in this case at the point A there is some pressure due to this height HA of fluid. And again we are saying this is open to atmosphere, so at the free surface of this fluid atmospheric pressure is acting. So now in this case when we are exerting, we are not exerting, actually we are connecting this Utube to this pipe here. So in that case, here at the point A, as the pressure is high, and this, if I'm supposing this, I'm saying that is this point is connected, or this end is connected to this tube, and at the A point the pressure is higher than this open end. In that case, the level at the one side, this is the one side, that is the left limb, if the pressure is higher than the atmospheric pressure, this level goes down, and in the right limb the level of the liquid is going up. Obviously in this case, because this is higher, suppose here I'm drawing this one and it looked like this one. Okay, these are connected, and this end is connected to some pipe. Okay, and initially the level was here when the Utube is not connected to this pipe. That was 1 and 2, and in this case we are saying that is at the point A, that is, if I'm saying that is PA, I'm indicating this PA is the pressure at this point A due to some liquid height or due to some other things. Maybe the tank is closed and the fluid is pressurized. So this is the pressure at the point A. Okay, this is PA, and this PA is actually P gauge, as we discussed. In this case, this is P gauge, and obviously as this is plus P gauge, as we are considering this is the first case when we are saying the manometer is connected to a pipe where at the center of the pipe the pressure is greater than the atmospheric pressure. So we are saying this is plus P gauge at the point A. Okay, so as this is plus P gauge, and here is atmospheric pressure and here is pressure more than the atmospheric, then the level of this manometric fluid will goes down here in this left limb and will rise in this right limb. Okay, so in this case the level goes down here of this manometric fluid and level of this manometric fluid is going up here. Just a minute. Okay, so in this case, as the pressure at the point A is the gauge pressure and this is obviously the positive gauge pressure, the pressure is higher than the atmospheric pressure. So in this left hand side or left limb, the level of the manometric fluid is going down here, and in this right limb the pressure is going to be rise. So the level of the fluid is going to be rise here. Now the pressure is not going to rise, the level of the fluid is going to be rise here. So it look like this one. Obviously this is not looking good. Now this is okay. So in the left limb the pressure is higher and in the right limb the pressure is obviously higher, so that's why the level of the manometric fluid is going to be down here and the level of the manometric fluid is going to be rise here. So and again let's suppose in this case the fluid in the pipe is lighter than the manometric fluid obviously here. So we know there is property of this manometric fluid is, we are saying the specific weight of fluid is Wm, and in this case that we are saying this is W1. Okay, so the new level difference is that I'm saying this is 1 dash and 2 dash. So initially the level of the manometric fluid at the 1 and 2, now I'm marking a line here, it's indicating 1 dash and 2 dash. Okay, now I'm saying this level difference, obviously here is the level of manometric fluid and in the right limb here is the level of manometric fluid, and I'm saying this is HM. This is the level difference of manometric fluid, and let's suppose for the fluid in the pipe or container is maintaining height H1 up to this point. Okay, and obviously here the exerted pressure is P atmospheric. But in this case we are saying that is at the point A the pressure is P gauge, because obviously this tank is open to atmosphere and over this tank the atmospheric, there is also atmospheric pressure here, and over this right limb there is obviously atmospheric pressure here. So this pressure at the point A, we are only considering the gauge pressure. Okay, so I think in this case the gauge pressure over here over the manometric fluid in the right limb is 0, because here we are only considering there is a pressure at the gauge point A is this much, and we are not considering the atmospheric pressure here as it is exerted over here over the tank here and over this side here. So in this case if you want to calculate what is the gauge pressure at the point A, then we know according to hydrostatic law that is at the same level the pressure intensity will be same. So obviously in this case at the point 1 dash and 2 dash the pressure intensity will be same. So we can say that is P1 dash will be equals to P2 dash according to hydrostatic law. Okay, so first we will try to calculate what is P1 dash. So P1 dash, obviously in this case P1 dash will be gauge pressure. So first of all, at this point A or the gauge point A, there is some pressure that we want to calculate, and that we are saying this is PA, that is unknown. Now at the same level the pressure is same, that is PA, but as we are going down in the fluid, obviously the pressure intensity increases, and in this case this is the fluid over here. So at this point the pressure will be equals to PA, that is the pressure at this point, plus, because the pressure intensity is going to be increased, and according to hydrostatic law, over the depth the pressure will be equals to W1 H1. Actually this is rho 1g, so this is W1 H1. So this is the pressure intensity at the point 1 dash. So P1 dash will be equals to PA plus W1 H1. Okay, so now what is P2 dash? So P2 dash, again I'm saying this P1 dash and P2 dash are the gauge pressure. That's why I'm not including here the atmospheric pressure. So in this case of P2 dash, we are not including atmospheric pressure. Okay, so the P2 dash is only due to this manometric fluid over here. So we can write the P2 dash will be equals to specific weight of manometric fluid into the height of manometric fluid, that is HM. Okay, now so from this condition, that is P1 dash equals to P2 dash, we can write that is PA plus W1 H1 will be equals to this P2 dash, that is equals to WM HM. Now both side the pressure is gauge pressure, but let's suppose you are saying that is this pipe is connected to some tank, and over the tank the atmospheric pressure is exerting. So the absolute pressure at the point A will be P atmospheric plus P gauge. So P gauge at the point A is due to the height of fluid over this point A. So that I'm including P atmospheric for the example. So this will be absolute at the 1 dash, but this is gauge. So for this case we can't compare absolute to the gauge. So in this case also, here at the 2 dash point there is atmospheric pressure, so we'll include P atmospheric. Okay, but again both side P atmospheric is going to be cancel out. So it is important point. Either you will compare both side absolute or you will compare the gauge. Okay, but if the conditions are different, that is the tank is pressurized and there is some extra pressure, then we will see in the next lectures. But in this case the gauge pressure at the point 1 dash and 2 dash, we are writing there is PA plus W1 H1. At the 2 dash point we are writing this is W1 H1. Now our unknown pressure at the point A, that is PA, now we can calculate and we can write that is PA will be equals to WMHM minus W1 H1. Okay, so obviously in this case we know the property of this manometric fluid and we can measure this height, and we also know the property of this fluid in the pipe, and we can also measure the H1. We can easily calculate what will be the pressure at the point A, that will be actually the gauge, by this one. Okay, so this is the Utube manometer. Now one more thing is important here. In this condition of Utube manometer, definitely the specific weight of this manometric fluid will be higher than this fluid, because in this case when I am saying this fluid is heavier than this fluid in the pipe, that's why this fluid in the pipe is floating over this one, because the density of this fluid in the pipe is lighter than this one. And if we are not taking a manometric fluid that is not lighter than the flowing fluid in the pipe, in that case, if this fluid is lighter and this is heavier, definitely this fluid is going to sink in this fluid, that is the manometric fluid, and manometric fluid is lighter compared to this one. This will flow inside the pipe and we can't calculate the system. So in this case of Utube manometer, the manometric fluid specific weight will be higher than the fluid in the pipe or container. So by using this one, we can easily calculate what will be the pressure. Now another one thing that is important is, as this fluid specific weight is higher than this one, then we can easily calculate the excess pressure values. How? Because we know, according to hydrostatic law, that is, let's suppose that is P atmospheric, we know, is equals to 10132.5 Newton per meter square or Pascal. So to maintaining this pressure, according to our previous lectures, we can easily understand, that is, to maintaining this pressure, the water required height equals to 10.33 meter. But if I'm using the mercury in that case, that if I'm using the mercury in this case, then the mercury only required approximately 760 mm. So obviously at this point 1 dash, as this is water, it will require more height, but at this fluid is heavier, this will require to measure less height. So in this case, by using this manometers, that is Utube manometers, we can easily calculate the higher pressure values. Okay, and in next lecture we will also understand how we can use the Utube manometers to measure negative gauge pressure that was not possible by the piezometer, and also how we can use the Utube manometer to measure the gaseous fluid pressure, that was also not possible by the piezometers. Okay, thanks for watching. Till then, take care of yourself. See you in the next lectures. Thanks a lot. And guys, please subscribe the channel, like it, share it, comment the doubt, and share the knowledge as much as you can. Thanks again.